Hello, I'm Jaeheung Park from Seoul National University, South Korea. Thank you very much for inviting me to this workshop on floating-based robots in manufacturing and logistics operations. The title of my talk today is Difficulties in Assembly Task for Floating-Based Robots. So what I want to discuss today can be seen from this illustration here. That suppose that we have one humanoid robot and one two-arm mobile manipulators, and we want them to assemble a chair or any other furniture, then what will be the difficulties for that, especially for floating-based robots? So in fact, I don't have direct experience on using these floating-based robots for assembly tasks. However, our group had a very recent project, and in that project we used 3 fixed-based manipulators for assembling a chair. So through the experience of that, I think we can see what would be the difficulties if we do the same thing for using a floating-based robot. So I would like to share the experience of our project. So this is the overview of the project. So we are supposed to assemble a chair starting from the instruction in figures. So we have to recognize the instructions in figures and find out the relationships between parts and assembly instructions. And these tasks were conducted by another university, GIST in Korea. And these instructions were given to the robot, and robots are supposed to assemble a chair using these instructions. And this task was conducted by our university, Seoul National University, our group. And in that project, there were actually 4 consortiums. And I want to introduce some hardware differences among the 4 consortiums because it was quite interesting to see the differences. So the first consortium was Korea University and Seoul-Mind, and they decided to use 2 large robots. Those are UR10, and UR10, 2 UR10 robots were large enough to manipulate and assemble all the parts. So I think that personally, I think that this is the most of the efficient way to do that using large robot, basically. Another consortium, Hanyang University and Kitech, they decided to use 2 medium-sized robots, UR5. However, those 2 robots were not large enough to manipulate and assemble all the parts. So they finally, in the end, decided to use moving table and tray so that they can move furniture parts or tools to be used for assembly. Another consortium was Kitech and KETI. These 2 are the research institute in Korea. They decided to use 3 medium-sized robots, RB5, from Rainbow Company. And these robots are actually similar size to UR5. So even if they used 3 robots, they were not enough to manipulate and assemble the parts. So they designed high degree of freedom robotic hands and moving table. And all together, they successfully finished the task, assembling a chair. And actually, in fact, they were the fastest among all the consortiums. So I think that using this nice high degree of freedom robotic hands and moving table were a very nice strategy to do that. Finally, our consortium, Seoul National University and GIST, we decided to use 3 medium-sized robots, Franca Panda. These robots, the size of these robots were similar to RB5 or UR5. So these robots were not large enough to manipulate and assemble all the parts. The reason that we chose this Franca Panda was to utilize the torque control capability. And for our case, instead of designing a moving table or high DOF robotic hand, we decided to use only simple grippers. And because of that, we had to choose we have to use complicated motion planning algorithms for handing over or constrained motion planning. And these were actually possible to finish all the task of assembling a chair. So our main strategy was basically the very first one is the torque-controlled robot and compliant motion control to deal with uncertainties, especially for Peginol tasks. So instead of using hand-eye camera, we thought that this torque-controlled robot could be used to deal with these uncertainties, and in fact, it was possible to do that. Of course, I think that hand-eye camera could have been better if we used it together. Constrained motion planning for multiple robots for tight but large workspace was another strategy instead of designing a moving table or high DOF robotic hand. And we also designed various tools and simple grippers for grasping and drilling and developed recovery strategies for failure cases. However, today in my talk, I would like to focus on the first two strategies because those are relevant to this workshop today. So I would like to introduce our experience through the videos mostly. So this video shows our peg-in-hole strategy with compliant motion control. You can see that the robot hold an L bracket and then try to insert it to hole. And our peg-in-hole strategy usually have 4 steps: approach, like now, and then search by spiral motion, and then if it is in, we are trying to have confirmation, and then if it is confirmed, then insert. And in this right now, we have another step to double check if it is correctly inserted by pushing one more so that it's really inserted very well. It's finished now. And then the next one was dual pin peg-in-hole. So the part has 2 pins, and then we are trying to approach to the other part of the chair. So this is side part. But before that, we are using kind of pose calibration using the gripper. So we are touching, holding the side part on one part and the other so that we are aligning the side part as we wanted them to be. And then we are approaching and searching and confirmation right now, and then insert. So those procedures basically we are trying to reduce the uncertainties due to the real world cases. Basically, when we hold, grasp, and moving the parts, there are uncertainties coming up, and we are trying to reduce them by holding the parts and having the peg-in-hole strategies with compliant motion control. So now this is a 3-pin peg-in-hole, so it's triple peg-in-hole, but they are grouped into two. So we have here 1 pin assembled and 2 pins are now we are wiggling to have them to be inserted very well because it's quite tight. And now the next peg-in-hole is very interesting and one of the most challenging tasks in our project. So now you can see that the side part of the chair is going to be assembled, and here you can see that so many pins. So I think there are 7 pins, but they are grouped into 4. 1, 2, 3, 4 groups. Now we are trying to assemble one by one, and here you can see the 2 pins are searched to be here into two holes. So we try to do it only one part here first, and then try to assemble all these three together later. And when we do this Pegino strategy, we many times have to understand if the robot is in contact or not, and what are the contact states right now. And when we do that, we mostly use the joint position information and forward kinematics. However, in many times we also use joint torque sensor. So because the Panda robot has a joint torque sensor on each joint, and then use the formula force is equal to J bar transpose gamma to compute end effector force, and those forces were used to uh, understand what are the forces applied on the end effector. And now you can see that the robot is trying to hold the parts of the furniture that are going to be used for Pegino. Basically, now we have 1, 2, 3, 4, 5 parts, but since these are assembled, right now what we are trying to assemble is basically this part with the side part of the chair, and this part and this part. So we want to hold this side part and this is back part and this part with three robots. So three parts, three robots, and then try to move around to align the pins with the holes. And during these operations, we have to hand over this part from this gripper to the other gripper. And now this is going to hold to assemble this part. So by the way, when we move these robots from one place to the other, we are planning in joint space and controlling in joint space. And when we do Pegino task, we are controlling in the task space. So now you can see that we are aligning all these three grouped pins all together and successfully inserted. So whenever it happens, whenever we finish this successfully, we are very happy. Although we were not successful 100%, but the success rate was quite high. Calibration of multiple robots for this assembling task was an unexpected problem, actually. So basically, the robot has redundancy because it has 7 DOF on each arm. And because of the redundancy, we have this property. For a given goal and effector position, we may have two joint configurations. But why this is the problem? So as I mentioned before, we are planning robot motion in joint space in many times when we move one part from one position to the other. And we are actually conducting this motion planning online. So at this moment, we plan from one place to the other, and we have a solution of Q1. And next time, we may have the same motion planning, but we are going to get Q2. However, when we execute it, we have different position X. Forward kinematics shows the same X, but actual robot position was different when we measured with rulers, basically. So this posed very serious problem. So that's why we had to do calibration. But it was quite difficult to do it for a redundant manipulator. And also, first of all, the more problem was basically for dealing with multiple robots because they have shared workspace. So we have to focus on this workspace to calibrate all three manipulators together. So what we have decided to do that was that we designed one metal part and all three manipulators are connected together here. and we know the geometry of this object exactly. And this shape and size was designed to be similar to the workspace of the robot, roughly. Uh, I mean, the similar shared workspace as we imagined, roughly, although it's not exactly. And we collected enough data by moving these three robots together as shown in this video, and used the data to calibrate the three robots, and those were most successful calibration parameters for this assembling a chair task. So this was really unexpected problem, but we successfully uh, solved this problem good enough. Maybe not is perfect, but it's good enough for this project. And another feature that we had was basically constrained and multimodal motion planning. This is because we didn't have moving table and moving tray or a high DOF robotic hand. So that's why we used the simple Reaper to move uh, partially assembled chair using three robots in this case, and we had to rotate to assemble the other parts of the chair. And during the time, we had to hand over and regress it in the air. So it was very, very difficult to plan. It was quite difficult to obtain a solution many times. And on the lower video, you can see that sometimes we had to move one part to a location which cannot be reached by one manipulator. Then we had to hand over, and that involves regressing. So whenever it involved regressing, the motion planning was quite difficult, and also the uncertainty increases. So these were our strategies to do that. So in summary, for this project, we used only fixed-base robots. And to deal with the uncertainties, compliant motion control was implemented using torque control robots, instead of using basically hand-eye camera. And of course, hand-eye camera could have been very useful, but compliant motion control strategy was only compliant motion control strategy was enough to finish this successfully. And among many difficulties, calibration and motion planning were quite critical and quite difficult in our case. Now, from this our experience in this project, if we want to move this same task to floating-based robots, then what would be the difficulties and what would be the advantages? This is the discussion in our workshop today. So I think the obvious advantages of using floating-based robots would be much larger workspace for moving parts especially. And because of that, we will be able to use smaller number of robots, and each robot would have more redundancy, so that would be very nice for conducting tasks. And it will require less regress, which will reduce the uncertainties. However, there would be many difficulties using floating-based robots. So one thing would be much increased uncertainties because of the floating-based robot. So compliant motion technology should be utilized. However, that would not be enough probably. Then we have to use SLAM algorithms with external sensors to reduce the uncertainties, and visual surveying with camera, hand-eye camera, probably are going to be needed. And calibration would be also much more challenging because we are going to deal with much high DOF robots with larger workspace, and floating-based robots can provide much more problem for that. And motion planning would be also more challenging because we have to deal with high DOF robots and many or much more uncertainty, modeling uncertainties. So I think we will have this and that advantages and difficulties. So I think this is the discussion point of our workshop, uh, going for floating-based robots for manufacturing and logistics operations. So I'm looking forward to discussing much more with other people for this topic today. Thank you very much. And you can see more videos in our lab YouTube channel. So you can search for Dairos at YouTube homepage. Thank you.